Hello, everybody. I'm sorry I don't speak any Russian, so I will have to speak in English. But it is my pleasure to be here today and tell you a little bit more about Panasas. Hopefully you've already heard of us at some point. But we did a lot of research in high-performance computing data sets over the last couple of years. So I'll hopefully have an opportunity to introduce Panasas, the company, but also share with you some of the results of our investigations into how people actually store data in HPC, and then explain how that knowledge led to the development of our latest product. So Panasas was actually started in 1999. We're now one of the three most commonly deployed parallel file systems in HPC, according to IDC. So we've been shipping products for five generations, still privately held, and growing every year. And here in Russia, we're represented by Storos as well as HP, and we've been growing our business here very substantially. You'll find us everywhere in the common industries that high-performance computing is found. Aerospace companies, automotive, energy, especially a lot of that here, finance, government, genomics, manufacturing, and of course, university environments. So globally, you'll recognize a lot of our customers as very substantial corporations and public sector and government institutions. And if you look at actually what we've been doing closer to here, Jose Carrera is here with Panasas as well, and you can find him at our stand or me to find out more about the company or our products. But you can see here that even within Russia and the Eastern European region, we've been finding very good success in a pretty wide variety of deployments. So obviously a lot of energy, some government, some manufacturing. So it's a nice spread of different industries. But they all have one thing in common, which is a lot of use of clusters and the need for storage. So one of the most important trends in storage right now is the adoption of flash storage, solid-state disk, and it has very different properties than large SATA drives or nearline SAS hard drives. Of course, the SATA drives are relatively slow, but they're very big capacity, and they're very good for throughput performance, but they're not very good for random access. And flash, of course, is much more expensive, but very good for that random access. So we really wanted to understand a lot more about how customers actually store, what do data sets look like in high-performance computing. So we used a Perl script called FS-stats for file system statistics. And we worked with our customers across the globe to get them to run this utility to get an idea of what's the nature of their storage. Many of them said that they really only care about large file performance and they really only have large files. Some others knew that they had a lot of small files, but pretty much across the board, people had many more small files than they thought. So this graph shows that for the vast majority of data sets, more than 60% of all of the data being stored is actually smaller than 64 kilobytes in size. So now, how much capacity does this take up? Maybe not very much, but it's very important to know that when it comes to a parallel file system or storage, the number of files being stored has a very big impact on the performance of the system, because there are a lot of activities that file systems have to do that are really by the number of files, not by how big they are. So here you see just how large a percentage of small files there are. But this is the other view, which is how much space do those small files take up. And the vast majority of the time, it's less than 1% of the capacity is taken up by 60 to 80% of the files. So you can already see that this is a very promising perspective when it comes to designing a storage system that combines serial ATA drives, and flash. There is some variation from types of companies. So finance companies, for example, tend to have the most number of small files. So these are the companies that are doing Monte Carlo simulations, for example, with HPC to predict stock trading. It's they have hardly any very large files. It's almost all small data. But the shape is actually the same as looking at a large government lab like Los Alamos National Labs in the United States. There they have single files that are 16 terabytes in size, for example, so extremely large files, but they still have a large number of small files as well. And you can also see that different file sizes have big spikes where they have tremendous numbers of files that are those same sizes. So that was just a little bit of an overview. There's actually a full paper that we published that goes into all this information in much more depth that you're welcome to read. But what does this mean for storage? It means that there's a very good opportunity to combine SATA disk with flash in a very useful way. So that brought us to the design of our product, ActiveStore 14, which is our 5th generation parallel storage appliance. So there are really 3 most important aspects of our storage. So it is a parallel file system, full POSIX compliant, everything that you would want, but it's actually delivered as a complete system. So hardware and software. Most of our engineers are actually software engineers because parallel file systems are very complicated to design and to support. But we can do a much better job with the quality of the product by developing the hardware with the software and delivering that together. As a result, we have leading performance in terms of the throughput per disk in the system that, as far as we know, is higher than any other system in the world today. We do that without the use of hardware RAID controllers or filer heads. So it's a highly parallel architecture. But we've accomplished that while having everything be extremely easy to use. So you can install in under 10 minutes and you can grow online just by adding additional shelves of our storage. And the reliability and availability is very good as well, all redundant, no single points of failure. The big difference in architecture is if you look at a traditional storage system where everything has to go through a filer head of some sort, that ends up being the bottleneck. So we have scalable metadata that's out of line. For example, if you're writing a very large file, you only have to talk to the metadata controller once, and then all the rest of the writes you're writing in parallel to multiple storage nodes at the same time. The RAID is actually done inside the client, not inside the storage system. So this means that if you have a very large number of clients, you also have a very large number of RAID engines. So we have customers that for example, use up to 9,000 nodes all at the same time talking to the single file system. And that works partly because a very small amount of the compute cycles are used for computing the RAID, so we have scalable RAID performance. And when the compute nodes wants to access the storage, it would be in an I/O wait state anyway. So using a little bit of the cycles of the compute node actually doesn't slow the compute cluster down at all. It actually speeds it up by getting it out of that I/O wait state. The product is actually a bladed design. So we have directors and storage blades. The director blades are for metadata, and the storage blades are obviously for actually storing the data itself. So you can have more and more metadata performance by adding more directors, and you can have more capacity and more throughput by adding more storage blades. Everything is connected with 10 gigabit Ethernet. We also have InfiniBand routers to be able to also connect to InfiniBand clusters. I would say probably more than half of our customers use InfiniBand, so that's an extremely common scenario for us. So here's what happened with the flash and the SATA. So our storage blades, you can see a picture of one here on the right, has 2 high-capacity hard drives. It has a very lightweight Intel embedded processor, a little bit of RAM memory as well for cache. But then we added a 1.8-inch SSD to the mix. So in our typical configuration, just a little bit more than, maybe a little bit more than 1% of the capacity is on flash. And what we use that for is we store all of the small files and all of the metadata for the file system on flash automatically. So you don't need to know anything about what kind of device you're writing to. You just see a one big global namespace. But when you write data to that file system, the storage system automatically sees if it's a small file or if it is metadata, and it writes that data to the solid-state disk. So the difference that makes is pretty tremendous. For example, small file reads or stats, for example, for metadata, are almost 10 times faster with this version of the product than the one before that did not have flash in it. So flash accelerates and makes faster all of those small file and metadata performance with a very big difference. Even file listings, so doing an ls -l to navigate a very big directory, that actually became 35 times faster because it's now being read off of flash. The other good thing about flash in this particular case is because it is only 1% of the file system capacity, it doesn't change the cost of the storage system very much. 99% of it is still SATA disk. So the dollar per terabyte of the solution still stays very interesting. And then finally, in terms of ease of use and management, there's a complete command line interface, obviously, but also a very nice GUI. You can tunnel down and see even like serial numbers of hard drives, firmware, all of that low-level information, the CPU load on each of the blades. You can really get as much information as you want about what's going on in the system. Of course, the health of the system. If there are problems with any of the blades, it's very serviceable. You can pull out a blade, put the other one in, it'll automatically rebuild. Our rebuilds are completely in parallel. It's distributed because it's done with erasure coding. And of course, just the upgradability, you just add another shelf when the first one is full, and the system will automatically rebalance all of the data across all of the storage. So as your system grows, your files stay completely distributed across all of the storage. That keeps performance high, but it also means that you have an even distribution of all of your data. And we have SNMP integration that you can use to go into monitoring tools, third party, a lot of enterprise features like snapshots and user group quotas. But this is the use of Flash in Active Store 14 is, I think, the first of many products to come for Panasas, where we're going to be increasingly using Flash storage in interesting ways. Even as a privately held company, we received investment money from Samsung Ventures this year, which is a very interesting partner for us on both an engineering and on a financial side, because they are the world's largest manufacturer of flash in the world. So expect to see a lot more from us in the years to come around flash, but already the reception that we've had for Active Store 14 has been very good. Universities, for example, using many different types of research and science at the same time, have found that the product containing solid-state disks has been able to deliver high performance to all of their workloads at the same time, which was something that they weren't able to see before. So it's making a very big difference for our customers. With that, I'll see if there are any questions. If not, you can also find either me or Jose at the stand in the hall. Okay.
Замечательно. Questions, вопросы? Так, можно по-русски, мы будем переводить. You may ask in Russian, to translate. Прошу по-русски. Используете ли вы вашу собственную версию кастом параллельных подфайловой системы или какой-то бренд? Там,
Yes, so Panasas has developed, this is our own parallel file system that we've developed for the last 14 years. So it's very mature. We've had a lot of time making it stable and reliable. Our founder, one of the people who started Panasas, is a very well-known scientist, Dr. Garth Gibson, who works at Carnegie Mellon University in Pennsylvania. He was one of the original inventors of RAID back in the 1980s at Berkeley, and then in the 1990s was one of the inventors of object storage. And that led to the development of not only Panasas, but also Lustre and the Google file system. So Panasas was Garth's company to commercialize and make a commercial company around the file system technology that he invented. The Lustre file system became an open source file system, not directly related to the Panasas file system, but the object storage concepts are actually in both file systems, and they both came out of Garth's research. So this is very much our own technology.
На одном из слайдов было сказано, что в вашей параллельной файловой, в ваших устройствах используется out of band meta object. Да, yes. Out of band meta data, yes. What is it means?
Okay. Okay. Yeah. It's not so good detail on this slide, but so the director. So we have two different types of blades in the system, and the director blades handle metadata. What happens? So we have a client. There's a Panasas client. It's an RPM that runs in Linux that you would install on all of your clients. And that tells, so the compute client knows which director to go to for a particular directory. And so it will go first to the director blade to find out what blades have information, have parts of a particular file. So if you're going to read a large file, that the metadata controller for that directory will tell you, go to these 10 blades or 20 blades or 30 blades, and then all of those reads will happen in parallel. So everything is stored as objects. So the clients, when you write a file, the client actually computes the RAID, creates a number of objects. The metadata controller tells it for that directory, tells it what blades to write the data to, and then that client will write all of those objects in parallel without any further use of the metadata controller. So usually, and keep in mind that we scale the amount of metadata as well. So you can have as much metadata performance as you want. But the important thing is that you don't have to always go through a director blade when you're doing your reads and your writes. So we want to keep the metadata completely out of band so that you're not going through the metadata controller. You're just using it for one or two very lightweight operations. And then if you're writing a large file, you're doing that completely without talking to the metadata controller anymore. So we get the good throughput by in that way. A traditional storage system, the metadata and the data goes through the same filer head, and then everything has to go through the metadata controller, and then it gets very slow. So the high throughput is really done by use the metadata controller very little, and then once it's done, it just all reads and writes straight from the compute to the storage. I hope that helped, but if not, we can talk some more. Yeah, so in terms of the industry, yeah. So these days we're seeing a tremendous, so I would say oil and gas exploration, especially seismic processing, is probably 30% of all of the deployments that Panasas does. But we have some other major ones. Obviously, a lot of government and university use. That's maybe another 25%. We also have a lot of use in genomics for life sciences, and a lot in manufacturing. So the design of everything from defense systems to aircraft and automotive, and there are a lot of those types of products that require simulation. Really anything that involves simulation on a cluster ends up making a very good fit for our storage. So that's just a few of the biggest examples. But obviously here we do a lot of business with energy companies especially. Okay. Thank you very much for listening. I hope I spoke clearly enough and slowly enough, but it was great being here.